Yeah, whenever one talks about turbulence, one would like to know, for example, the correlation scale which you mentioned through pictures, and also the correlation time. In the sense that if you take two time slices, two times your simulation and see what's the decorrelation time. That would also be an interesting thing to. When I first looked at these simulations of Norman and this thing, when I was visiting in PA at that time, I was never kind of sure whether these are just motions or where is the turbulence. And I would like it to be turbulent, but it would be an
according to me, those kind of motions sketched in the paper by Norman and so on was simply large-scale accretion, and much of those curling motion was some kind of sloshing around the core of the cluster, but they were not real turbulence. But turbulence there was in the shear interface.
So where is the turbulence in your case?
In our case, you can resolve much more cooling like motion, but they are not driven by dark matter structures. They are just curling or fluid dynamical motion, but they are not driven by a real clamp. Perhaps we can show you. This is one typical map. You can have those large scale motion that are due to some structure doing its how to say,
motion. Yeah, I mean, one would like to know after some time whether they disappeared and decorrelated somehow. Or,
you can follow the evolution of that. I never evaluated the correlation time of that because it is not easy to say who is who after a time has passed.
Correct. So you just take two time slices and correlate them.
I never did it, but because the other complication is that you continuously have injection, so it is not a stable box that you can just simply follow, but you have, for instance, next time step of the simulation, you would have another clamps entering here, so
that's turbulence.
Okay, last question.
Okay, the question is related to this. So, in such simulation, is it possible to detect formation of large-scale structures in velocity field by generation of large-scale vorticity?
Yes, I mainly did.
Is it turbulent structure or large-scale?
It's a random structure, or more or less regular.
If you have maps of such velocity field and average over 100 maps, is it possible to observe here?
In principle.
Structures?
Yeah, I never did so far with large-scale velocity field. So I mean scales on the order of filaments and so on. Dom Surrillo did that with Eulerian simulation and found some very regular pattern in terms of curling of color velocity around galaxy cluster, which is driven by filaments and so on. So it found a very regular pumping, but I don't know, it's on scale of megaparsecs, so I don't know how to call it, because if you look at it, you have a continuous inflow of matter, so it is not clear to me if it is a gravitational driven motion, a fluidodynamical motion without pump, I don't know.
Okay, thank you. Okay, so our next talk is by Andrej Balkans. We're going to not talk about the thing he was going to talk about, perhaps. I don't know, looking at the book. His title is Measuring the Structure in Magnetic Turbulence by Synchrotron Polarimetry.
So I'm actually going to talk about that, but first I talk about this, okay? So I didn't want to talk about, I was not supposed to talk about it, but my supervisor insisted, so what can I do? Right? So this...
Who is your supervisor?
Torsten over there. So the common theme of the talks is that we're trying to characterize astrophysical magnetic fields. And in these first presentation, what I do is I speak about a code which we developed, which simulates galactic synchrotron emission. Synchrotron emission, we heard today a talk about this emission, which is considered more complicated physics. Synchrotron physics is much easier. It's easier to understand. You know, it's simpler, and it's a very good tracer of the magnetic field. And what we aim to do with that code is, of course, you have a tool which is capable of confronting models with observations, because out of this code we are going to generate mock observations, which we then compare to real observations. And, well, the second part we will see soon. All right. So what does this thing do? That's shown in this slide. You have a bunch of input parameters, right? So you have your standard, whatever, cosmic ray electron distribution for your galaxy. You have your magnetic field model for your galaxy, and these things will generate the synchrotron. Yeah, these things will generate the synchrotron emissivity, which you see in these things here, right? And we also consider Faraday depolarization effects. Thus, we need to compute the rotation measure, which you see here. And for that, we require a thermal electron density model. Okay, cool. The things in color are going to be your input parameters, and as an output, you're going to get synchrotron total emissivity and polarized emissivity, which essentially is our IQ and U Stokes parameters. We have no V Stokes parameters since the synchrotron emission is partially linearly polarized, hence no circular polarization. And we can, by default, also compute rotation measure maps, because it's a necessary input for all that. Good. What can you do with that? That's an example of such an output. What you see here is a full sky map of, well, a full sky map. And along the equator, you have the galactic plane, and you see that this is polarized intensity, and you see that as you approach the galactic plane, where there is more thermal electron, there's a higher thermal electron density, you are going to have stronger Faraday depolarization. So you see sort of fancy structures you have here. The magnetic field we used to generate this picture comes from a paper by Page and collaborators. That's essentially the WMAP magnetic field, which was designed to reproduce this observation. Okay? So the left-hand side is an observation, and the right-hand side is a simulation. What you're looking at here is the polarization angle. So Marijke, a couple of days ago, showed us, or actually yesterday, showed us a map which contained the polarization direction superposed with the total intensity. Here, in color, you just see from like blue to red, you're going to see 0 to 180 degrees, and this is an observation. So the model they used for their magnetic field reproduces that remarkably well, right? I mean, you evidently see that this thing is very similar to this. Okay, so, however, the message which I want to pass you is that if you are trying to constrain your magnetic field, which is our objective in that case, you should try to adapt this field or to check this field with as many observations as possible. And that was done by a recent paper by Xiaohu Sun, Wolfgang Reich, and Thorsten and myself, where what they do is essentially they apart from, they don't just look at the polarization angle, they also look at rotation measure profiles. So they do what? They go along the galactic plane and take a longitude profile of the rotation measure. You have the observations, which you see these points with error bars here, which are available. And they essentially take this model, the WMAP model, which was given in. They take the thermal electron density distribution, which is widely accepted nowadays, which is this Cordes-en-Lazo, although people criticize it, they still use it. And you see that here clearly this black curve, which is coming from the model, definitely does not fit these observations. However, if they use a model which you see above here, in that picture, there are actually two models like that, but that is one example. If you use that model up there, then you certainly are going to have a much better fit to these points. So keep in mind, this is a trial and error approach, right? So this is no parameter scan, so this is by way. It's still not a complete answer for sure, but it shows that if you are trying to constrain this field, we need to use as many observations as possible to do so. Another particularity of their field is that they had to account for here you have longitude profiles of the rotation measure. If they did, once they did latitude profiles of the rotation measure, they also noticed that they had a necessity for an extremely strong toroidal halo field. So it's a field which is a bit above the galactic plane and a bit below the galactic plane, which is a field of a couple of microgauss, so something like close to 6 microgauss, to explain the latitude profile.
So these are two spirals superposed? Or?
This thing here, this is just one spiral, and then they have a stronger ring built inside. They have another one which is essentially a spiral, and you have an arm coming out in an opposite direction coming out of the spiral. In fact, these models are generally very degenerate. They noticed, in fact, Xiaohui and Wolfgang, they noticed that this observation here can be reproduced with pretty much any magnetic field model you have in the literature at the moment. So it's not very constrained, since this is pretty degenerate. Okay, so if you have more questions about that, please ask me later. And now I can go to what I originally intended to talk about, which is this thing. Right, so this is work done in collaboration with Alex Shikoshihin and with Thorsten. What I'm going to tell you, what I'm going to speak to you about is an attempt to characterize magnetic fields. So what we're going to do is we are going to look at observations and see if we are capable to extract from these observations some sort of constraint on what magnetic field we are looking at. And the quantity which I'm going to talk to you about today is like two things. I'm going to talk about our observables, which are Stokes parameters, and I'm going to talk about this quantity which we are trying to measure with these observables, which is the tension force, which characterizes your field in a particular way, which is what I will explain you. Right, so outline of the talk goes as this. First, I show you what sort of scenario we are speaking of, what is the observation supposed to look like. I will tell you what the tension force is. Most of you will find that most probably a bit boring, but nevertheless I will go through it. I will tell you what it tells us in special. I then will show what our work actually is, which is this third point here, which is, yeah, okay, can we observe this tension force? So I will summarize, and then I will show ongoing work, which is essentially a test on how sensitive this method actually is. Good, so this is our sketch of an observation. You have this blue magnetic field somewhere out there in space. It will be in a region where there will be cosmic ray electrons, hence this will produce synchrotron radiation. We will line of sight integrate that. This is this little dotted line, and we're going to get our observables, which are our IQU Stokes parameters. Good, we are interested in understanding this blue magnetic field in there, right? So let's take a look at a slice of how this thing is supposed to look like, or what we expect it to look like, and that is something like that. So the point of this slide is, as you know, since you have spent some time in this conference already, it's not a trivial structure, right? So if you're trying to characterize that, we need to do some sort of statistical analysis of that image. Right. So traditionally, what's the most basic thing which one can get at is naturally the magnetic field power spectrum, which is what you see above here. And in fact, where our field, our image, which we saw in the previous slide, where it is Gaussian, then we would be done, because we have a 2-point correlator, we have the power spectrum, and essentially that characterizes the image with everything we need. But in fact, you see these sheet-like structures, which most of you who do simulations know that that's what you expect. Then this is definitely not Gaussian, so this is not sufficient. What I'm going to talk to you about, of course, there are several other possible statistical ways of analyzing this map, but what I'm going to talk to you about is the tension force power spectrum. Right, so what is the tension force? Tension force is just a piece of the Lorentz force. This is this thing here at the end. And what does the tension force tell you? It measures the change of the magnetic field along its own direction. How can I visualize that? One can think of it like this. So I have drawn a cartoon here, and in the left-hand side, you have a very smoothly changing magnetic field. So it has a variation along its own direction, which is constant. So in this color, this orange color, you see what is supposed to be the strength, the intensity of the tension force. While on the cartoon, on the right-hand side, you have mostly the field is going straight, so there's very little change along its own direction, but then suddenly it turns sharply, and then turns sharply again, and so forth and so on. And this sharp turns will indicate a stronger tension force intensity. So what is the point here? If I'm going to do some sort of statistical analysis of these orange map and of these yellow and red map, then I should see differences. So yes, if these statistics can tell me this difference, then I'm capable of differentiating between these two scenarios in space. Right, so to put that point a bit even clearer, here I have shown two slices of, this is a simulation by Alex again. I have here two slices of simulations, which I'm showing you. So this one is clearly a simulation like you've seen before. And on the right-hand side, we have a Gaussian random field. Qualitatively, of course, they are different. You can see that by eye. And what we're looking for is a quantitative way of telling the difference between these two things. So what they have in common is actually the magnetic field power spectrum. So that's the magnetic field power spectrum. It's identical for both of these simulations. In fact, this simulation was generated with the power spectrum of that one. So with the magnetic field power spectrum, we cannot differentiate it. However, if we come to the tension force power spectrum, there is a clear quantitative way of telling the difference, right? You see here in black the tension force of the structured field, while you see in blue the tension force power spectrum of the Gaussian field, which is essentially a field with absolutely no structure. Right, so now I have spoken to you about the tension force. This is known, this is not new for most of you. And now I'm going to tell you if this is actually possible to observe, which is what essentially the word here was. So again, we are back to our observation, and our observation consists of a cube like this, which is synchrotron emitting. We're going to line of sight integral it and obtain our Stokes parameters that was displayed in this next slide. Here you have your Stokes parameters, I, Q, U, as a function of their position on your map, of your observation map. And you see that here we had two assumptions which we used. First, that the power law of the energy distribution of our cosmic ray electrons, the energy distribution of our cosmic ray electrons is actually a power law, which is not very unlike what we observe in our own atmosphere, and that we have a spectrum index on this power law, which is equal to 3. This is again not unlike what is observed in our own galaxy. So what does this generate? So why is this point important? Why am I addressing these assumptions which we're doing here? Because this causes these magnetic fields here, in these integrals again, to be always fields to the power of 2. Okay, so you have here a bx squared, a by squared, same thing here, and here you have bx by, right? So if I'm now going to, for instance, start doing correlation, because that's what I'm going to do if I'm doing statistics, I'm going to correlate, for instance, my I Stokes parameter with my U Stokes parameter, then I should have a 4-point, or a correlator which contains 4 magnetic field pieces of magnetic field, which you see in this point here. So I correlated my I Stokes parameter with my U Stokes parameter, and I'm cutting the notation down to this. I promise it's the only notation cut which I'm going to do here, right? So this is going to be a 4-point correlator. You see, so you have as we come back to the previous slide, you see that you have here your bx squared, so it's going to be xx, and then xy, and it's going to be yy, and then again xy. That's precisely what you see on that slide here. So fine, so that's the way it looks. These are the building blocks of these Stokes correlators. How does the tension force look? The tension force, since it comes from something like B grad B, it's also a 2-point, well, it's also is going to be a 4-point correlator in the end. And we are here, we are here in Fourier space because it facilitates computation. We don't need to bother about derivatives and integrals and so on, because they turn out to be either 4 factors or anyways. Okay, so what do we do? Let's compare our tension force, which you see here again. This is our tension force. It is composed of this sort of building blocks, and these are all our possible observable correlations. And all of them have this sort of structure which they come from this 4-point correlator. So fine. Does it mean that we can describe this tension force as a function of these observables? Well, there is a suspicion. Let's check. It turns out that not. The blue part here I just wrote the tension force power spectrum, right? I wrote it down explicitly. And the blue part, which you see here, will be describable as a function of observables, while the red part is not describable as a function of observables. And in fact, here you have the blue part described as a function of observables. Don't bother about the expression, just see that Here you have all of observables, and this is the blue part, right? So we are describing it as a function of observables. The red part is not describable as a function of observables. And why is that? That's a simple problem, which is the following. This red part contains 4-point correlators, which contain magnetic field components in the line of sight direction, which is this Z direction here. And all our observables, which is essentially a consequence of the fact that we're looking at synchrotron radiation, hence synchrotron radiation contains no line of sight information, do not contain information of the magnetic field along the line of sight. So we are stuck. We have shown that it's impossible to describe the tension force power spectrum as a function of observables at the current stage. So we need to assume something extra, and what we do is we assume isotropy. We are going to deal with two cases here, just simple isotropy, and then a very particular case of isotropy plus a very weak magnetic mean field. So we are taking a completely isotropic field and adding it on top of a very weak magnetic field.
You could use the rotation measure.
Second?
You could use the rotation measure.
Yes, but this would make the computation somewhat more difficult. Yeah. So, yeah, in fact, I mean, this is assuming that we are at high enough frequencies such that we can ignore the rotation measure. Right, so...
Model of the homogeneous operation. How is close to reality?
We don't know. So, how do we break down this 4-point correlator, which we see here? So I'm not going into details of this thing, but some of you maybe know that since whatever, kindergarten or something, but to me it was very non-obvious. But we use a thing called the invariant theory of isotropic tensors. This is old stuff. This is known since 1940. And essentially what you do, there is a generic way of describing a 4-point, 2-point, whatever correlator of an isotropic field. And here you have the expression for a 4-point correlator, assuming isotropy. That's what you see here. It will be a function of 7. You come down to this 7 independent scalars. And once you start putting in your here you have your indexes. Once you start putting in your x and y's and so forth and so on, it will be shown that some of your 4-point correlators actually are a function of combinations of your other 4-point correlators. Thus, you should be able of, if you're lucky, and we are lucky, to describe even correlators which even correlators which go in the z direction as a function of correlators which stay on the plane. And that's what happens. So we go back to our red part, which was previously undescribable as a function of observables. And here we have it described as a function of observables. So these two other items I just show you that, yeah, that's the way it does. Okay? If you break these things down according to the invariant theory of isotropic tensors, you get these two things which corresponds to the same breaking down of your Stokes correlators. Alright, so we managed to get our tension force power spectrum, right? Because now we are capable of describing the whole thing as a function of observables. And what does that mean? That means that now we are capable of discerning between this scenario and that scenario, thanks to the fact that we now are capable of describing the tension force power spectrum as a function of observables. Good, so now we make it a bit more complicated. Keep in mind, this is a very particular case where what we do is we take a completely isotropic field and on top of that add a mean field. Okay, so the field which, so how do you do that? Essentially you have your magnetic field here and it's broken down in a mean field plus variational piece, and effectively what it does, it will add to you, instead of your original 4-point correlators which you see here, you will also get your 3- and 2-point correlators. You apply precisely the same sort of procedure we did before, it's just considerably longer and whoops. But it amounts to the same, and again, you're capable of describing your P2 part of your tension force power spectrum as a function of observables. And finally, out of that, you again get your tension force power spectrum. And extra to that, it turns out it's also possible to obtain the magnetic field power spectrum. So I'm sorry for the notation, this M1 here should be precisely these, the power spectrum of the magnetic field. Okay, so the power spectrum of the magnetic field can also, in that very particular case, be described as a function of observables. Good. Okay, so that summarizes what the concept I tried to pass to you now, right? So we have our observation, it's going to generate observables, these IQUs, and start correlating them. Correlations of them, assuming isotropy, actually describe my tension force power spectrum, which you see here, which tells me something about the magnetic field, which essentially brings me new knowledge about my object in space, or it constrains knowledge about this object in space. Good, so this is all nice and good. So we have a method which we have shown on analytically that, yeah, it's possible to obtain that sort of information, but we would like to be able to assess what the error bars are on this method, right? How sensitive is it? How good is the statement of that method? And to my knowledge, yeah, okay, so to my knowledge, the only way of doing that is essentially picking a bunch of simulations of several different possible MHD scenarios, applying these mock observations, because out of the simulation we can directly compute our tension force, applying this method on top of on the mock observations and seeing how close it actually is to the true tension force per spectrum. That is what we did here. So again, we have this simulation and that simulation. I start with our Gaussian simulation because it's the point of the Gaussian simulation is of course not expected to be the case in space, but it's very simple to generate and very fast to generate, so it's computationally easy. So what you see here in red is the expected tension force, meaning it's computed directly out of your data cube. And in black, you see the first attempt, so if after one realization, how good does it fit that curve? And you see there is some fluctuation. And if you actually average over several realizations, which is the case for the blue line, then it gets much closer to the red line. So now this is dangerous, because we are dealing here with a Gaussian random field. This is the most boring possible 4-point statistic which you can have, because it's a field without structure. So, of course, we need to test it on our simulations which actually have structure, which is what is done here. After one realization, you see this blue line, and it, well, it's not, it fluctuates around the result, but it definitely contains a lot of, well, we probably need to average it over several more realizations, and that is going to tell us essentially how large does the cube in space need to be that we actually get a significant statement by such a measurement. And I stop here. Thank you very much.
Thank you, Andre. We have time for a couple of questions. I have one. So if you go back a couple of slides where you showed the difference between the Gaussian one and the filamentary, yeah, that one is it. Yeah.
Sorry.
Yeah. So one of the things that differentiates this from this is the phase information that you throw away whenever you take a spectrum. Right? If you do an FFT, this has non-trivial phase information, and this one has randomized phase information.
Precisely.
Is there any way, without trying to calculate tension, of keeping the phase information, doing the measurement and keeping the phase information? Because then you can get information not just about the places where you're turning sharply, but you might be able to differentiate between the fields just using that.
So I mean, you need something which is larger than a 2-point correlator. Any 4-point correlator, no matter what, is going to give you some sort of information about the phase in this thing.
Yes, some. Yeah.
But what information?
So how much do you need? I guess how much correlation? 4-point to get these phase information.
This I don't know.
Okay.
You make quite good comparisons with the test case, but still, differentiating observational data, noisy, is the last thing one would ever do, right? Meanwhile, there are, and I'm going to discuss in my talk, and also Andrew Bagley will be discussing it, another measure, which is called Minkowski functionals, which are morphology indicators, which include information on all orders of correlation functions. Instead of at the cost of differentiating observable data, getting perhaps information about the 4-point correlator, there is an excellent integral diagnostic which includes information about all correlators of all orders. I would perhaps we should discuss it. I would think that this is a dangerous procedure, differentiating observational data. Just 2-point correlation functions are difficult to estimate for observations.
Yeah.
I am aware of only a few partially successful attempts to do that.
course, you can't naively apply this directly to noisy data. You have to build a proper estimator, like a maximum likelihood power spectrum estimator for this force field, which then corrects for the noise, or corrects and also transports uncertainties introduced by the noise into the result.
But you can do by integration, not just by integration. Same information can be obtained by integrating this data and differentiating.
So you can tell us the force power spectrum.
Why you need power spectrum? In this case, power spectrum tells you nothing, exactly as Steve, because there are phases.
The force power spectrum. The force, the tension force.
Why you need it?
Well,
Why you need the force?
It's interesting. It's the dynamic quantity of the MHD system.
But if you could reproduce the fields, you can reproduce the force in physical space. Why, I guess I would ask, why do you need the spectrum as opposed to the thing in physics?
I would say it's the one we managed to get.
Okay.
That's a good answer.
I don't know if we can get more information out of it. So that 10 would be, that's as much as we got out of it. I don't know if it's possible we can get more. I wouldn't know how.
Okay, Nathan.
Please say again. Left picture is from Shikachiki and comes from calculation, but on the right hand side, what is it?
This is just a Gaussian random field.
Gaussian random field. And what about the scales? Is it more or less the same integral scale in two?
It contains the same power
We have the
spectrum.
same spectrum.
It's the same spectrum.
It's the identical power spectrum. So the power spectrum I used to generate
It is
this.
Gaussian, it is.
Yeah. So
And what I would like to be more or to precise, the scale, energy contained scale, the same in these two pictures.
yeah.
Amazing.
Yeah, no, just a comment that in the structure formation community, there has been tremendous interest throughout the years on trying to recognize things like filament, sheets, and all. Torsten, of course, knows all of it. So that, in particular, there's, I think, set of papers by Peter Coles looking at the phases, the phase information, which what Steve pointed out, and it may be worth. Now I remember that he did something on this, and it may be worth looking at that kind of stuff.
I'm not aware of these things, but
Yeah.
Okay, so let's thank Andre again. Get some coffee and we'll reconvene at 11.
Using specific imposed flow patterns, they seem to suggest that even in the kinematic regime, alpha has a strong RM dependence and even changes sign. So you don't have such a simple relation between the alpha and the helicity of the flow. We are going to examine this through direct numerical simulation. The second thing is how does the Lorentz force affect these turbulent transport coefficients? And it has been argued since long back that because of Lorentz forces, the alpha effect gets renormalized by the addition of this magnetic alpha, which is proportional to the current helicity of the small scale field. Now, there are papers by Proctor and Radler and Reinhardt which say that the alpha effect depends only on the velocity field, albeit one which is a full solution to the momentum equation. So, in this talk, I will motivate a simple analytical model to clarify this issue. So, these are the 2 points that I'm going to dwell upon for the rest of my talk. So, the first thing is, of course, the kinematic alpha effect, where we ask the question whether we can at all relate the turbulent transport coefficients to the statistical properties of the flow. So, in this part, we'll perform numerical turbulence experiments where alpha and the turbulent diffusivity eta t are going to be computed using mean fields as test fields of different spatial structure and in different direction. So just to give you a brief overview of what this test field procedure is all about, so if the mean field is sufficiently smooth, then the mean EMF can be expressed in terms of the mean magnetic field and its first derivative in a manner which is well known. So what we do now is we employ two-dimensional averages, x and y averages, such that the mean fields are only functions of z and t. If you further employ the solenoidity condition for the mean field, you realize that bx and by are the only two non-trivial components. And therefore, you are left to compute the various components of alpha ij and eta ij3, where I and j can run from 1 or 2, and in total you will get 8 unknown coefficients. So in order to determine these 8 unknown coefficients, you will require 4 different components of a test field. So this might look all pretty vague, so I'll start by giving just a simple example. So let us consider for a moment that you have 2 test fields, where, say, the first index of the superscript tells you whether it's a cosine mode or a sine mode, and the second index will tell you whether the non-zero component of the test field is an x component or a y component. And here K1 is the smallest non-vanishing wave number in the box that we have. So what we do now is we insert these test fields into the following relation, and you can actually go and find out that for each value of I, you will obtain independent matrix equations of this form. So here M is given by this, and it has a determinant of 1, so the inversion procedure is trivial and well defined. So given this form of the test field, we can now compute the mean EMF using the evolution equation for the small scale field, where here the term G is a nonlinear term, which you will normally neglect when you do a first order smoothing approximation, but it will be retained in numerical simulations. So in addition to that, we also have the momentum equation. Now, the simulations that we have done, what are the characteristics of that? So first point, there is no Lorentz force in the momentum equation because we want to look at the alpha effect only in the kinematic regime. There is no mean flow. We use stochastic forcing, and for our purpose, we are going to use resolutions from as low as 64 cube to as high as 512 cube using the pencil code. So we are mainly interested in the dependence of alpha and eta on Rn, and therefore we are going to consider cases where Rn is small, or, of the order 2.2, or where Re is 10 times Rn. So in a graphical view, this looks like this. So you either go straight up 90 degrees with Re of 2.2, and here the highest magnetic Reynolds number is around 228, or you go along the curve, or you go on a straight line less than 45 degrees with a magnetic Reynolds number of 0.1, and here the highest Re is about 180. So with this, I move on to whatever results we obtain, and the results that we obtain, we normalize that by using these expressions. So these are the foci expressions for alpha and eta t at high magnetic Reynolds numbers. And here tau corresponds to the correlation time of the turbulence. You can now define a Strouhal number of this form, and using the fact that for large enough Rn, Strouhal number is 1, you can actually write down alpha and eta t in this form. So having done all this, let us now look at a time series of alpha and eta for a high Rn but low Re. So what you see from this graph is this is a plot of the alpha by alpha naught as a function of the time, and here the time is plotted in the units of the eddy turnover time. And there are three lines. The first and the third one, beginning from up, will tell you are the corresponding error estimates, and the middle one is the running time average. So what you find is towards the end of the simulations, there are these fluctuations which are developed, and if you continue it for long time scales, these fluctuations can even become negative. So, but still, the running time average is close to 1. At least in this case, it is seen to be it is absolutely 1. So, and we believe that these fluctuations are because of the small scale dynamo, but probably they do not make a correlated contribution. Otherwise, the running mean could have been greater than 1 or less than 1 or whatever. But nevertheless, it makes the calculation of these averages more difficult. If you want to look at how the field looks like, so this is something what it looks like, and you can clearly see that the magnetic field is at very few places, it is very intermittent, meaning that it attains large positive and negative values only at very few places. So now comes the real thing, that what is the dependence of alpha and eta t on Rn, and we find that both alpha and eta t appear to be independent of Rn for the parameter regimes that we have considered. So this plot is for Re of 2.2 and varies with Rn. So you can clearly see that this is close to 1, and here the error bars are magnified by a factor of 2. If you do it for the other case where the Prandtl number is 0.1, you get similar behavior. So the inferences that we draw from here is, for isotropic turbulence, first order smoothing approximation gives quite accurate expressions for alpha and eta t in the kinematic regime, given that in the recent years, mean field dynamo theory has been questioned based on numerical simulations. We believe that the kinematic results obtained using foci do not appear to be flawed for moderate RMs of 220. Now, I come to the next part of the talk, where we'll talk about nonlinear back reaction and ask the question how this alpha effect is affected by Lorentz forces. So here, what we do is something very simplistic, something very uncomplicated. We assume that we are considering a regime where both the Reynolds numbers are much, much lesser than 1, and hence you can apply first order smoothing approximation to both the induction equation as well as the momentum equation, and you can get rid of those nonlinear terms G and T, which are often referred to as a pain in the neck terms. And for simplicity, we consider that you have no mean flow and a constant mean magnetic field. And since we apply first order smoothing approximation to both the induction equation and as well as the momentum equation, we refer to it as double first order smoothing approximation. Now, you might say that, okay, all this is fine, but this is pretty useless because for most astrophysical situations you have Rn much less than 1. But what I'm going to show you is that it nevertheless allows to make certain unambiguous statements about this difficult problem. Now, in the original paper, we have done it both for steady forcing as well as time-dependent forcing. But for time constraints, I'm going to talk only about this time-dependent forcing. So, you apply first-order smoothing approximation to both the induction as well as the momentum equation. And now, since you have thrown out all the nonlinear terms G and T from these respective equations, you can solve for U and B completely in terms of the forcing function. And this is how they look like. It is that simple. So, in order to compute the mean EMF, you still need the force-force correlation function. And then, of course, the turbulent EMF can be written in these forms in the Fourier space and as well as in the coordinate space. So, given the fact that you have neglected the nonlinear terms G and T in your equations, it allows you the freedom to compute the mean EMF in a number of different ways. The first one, you start from the induction equation and you solve for B in terms of U. And then you express the EMF completely in terms of the velocity field, as one normally does under first order smoothing approximation. And then you substitute for U in terms of F. So this is the first approach. The second one, you directly compute U cross B, since you know the solutions for U and B in terms of F. And this is what you will normally do in numerical simulations. The third one, you start from the momentum equation and you solve for U in terms of B and F, and then you substitute for B in terms of F. And the fourth one, we do something similar to what one does in tau approximation closures. You start by computing the derivative of the mean EMF. So I'm going to present the results that we obtained for all these various approaches. The first one, you start from B in terms of U and then you find the mean EMF in this form. At this point, you can express the mean EMF completely in terms of the velocity field itself, and you can recover the result that for isotropic velocities, the kinematic alpha effect can be expressed purely in terms of the helicity of the velocity potential. So this is what Radler and Reinhardt also obtains. Using a force-force correlation, you can express the mean EMF in this form, where there's a parameter n bar sitting here, which determines the importance of Lorentz forces. So if you are looking at a regime where Lorentz forces are unimportant, you can simply put it to 0. The second one, you compute the mean EMF directly, and you get something similar to this. And after doing all those rearrangements and all that, you will find identical expression for the mean EMF. The third one, you start from the momentum equation, and you express U in terms of P and F. And then if you compute the mean EMF in Fourier space, you see that there are two terms. The first term is an FB correlation. The second term is a PB correlation. And you can actually write down the second term for isotropic small scale field as the magnetic helicity, the real magnetic helicity. And if you express this in terms of n bar, so this looks something like this, and there are a few consequences that are important. So for n bar, mod n bar much less than 1, the first term goes over to a kinematic alpha effect, and the second term vanishes. And in the other regime where n bar increases, this term decreases and this term gains in importance. But since it has a negative sign, it tries to cancel the effect of this term. So it is similar to the suppression of a kinetic alpha due to the addition of magnetic alpha. But if you add these two equations, you get the same expression for the mean EMF. And that is not surprising because the starting equations are the same. The only thing that we have done is we differ in using, it differs only in the sequence of using the ingredients. That's all. So, and the nonlinear alpha in the limit of delta correlated forcing looks like this. In the asymptotic limit, it goes as P0 to the power -2. So, what we find is you obtain identical expression for the total alpha from all the three methods, provided that you take the FP correlation into account. If you do not take that into account, you are not going to get it. And it is explicitly apparent in this case that you can express the alpha completely in terms of the velocity field as a kinetic alpha, or you can express this in terms of the summation of alpha f and alpha m. Okay, now I move on to the fourth method where you start by computing the derivative of the mean EMF, and this consists of these two terms. The crucial questions that we want to ask is, we have seen from the previous slides that the FP correlation is important to get the correct answer. So does it really contribute here also? And in particular, can we ever recover this expression alpha k and alpha m together? So we start by taking the derivative of the mean EMF, and these are some familiar expressions. Okay, the next slide is a bit horrendous, it's a bit horrifying, but don't go away. So these are very simple equations. So you start by defining the mean EMF in this form, and then you define the alpha as a component of V naught, as a component of this thing, and you can compute the respective alphas, alpha k, alpha m, and alpha f, where the phi is just the correlator of these things. So what we get from here is, if you add the individual alphas, the total alpha is the summation of all these three for a generalized forcing function. And this matches, and the expression for the total alpha matches the expression for the alphas which you have derived from the other three methods. Now, the interesting case happens if you consider delta correlated forcing. So there, the explicit evaluation of this integral for the f cross p correlation gives you alpha f equal to 0. And hence, you can express the alpha completely as a summation of a kinetic alpha and a magnetic alpha. Given that the alpha f equal to 0, this thing was assumed in MTA calculations at large Rm and Re. But nonlinear alpha is still the same, and it goes the same behavior. So these are the theoretical plots of it, and if you want to make plots using numerical simulations at low Rm and Re, so these are results from numerical simulations at Rm and Re of 10 to the 2 into the minus 2. So quite consistent. So the inferences that I can draw from here is you can express the nonlinear alpha effect in several equivalent ways. You can think of it as in terms of the velocity field, and also in the nonlinear regime, we see that the alpha effect gets suppressed. The FP correlation is crucial for obtaining the correct expression for the mean EMF. On the other hand, if you do a type of closure which is similar to tau approximation, what you get is the individual alphas add up to give the total alpha, which is the same as one obtains from these two methods. But if you specialize to a case of delta correlated forcing, the alpha F term vanishes. So the total alpha is then just a sum of a kinetic alpha and a magnetic alpha. So to conclude, for isotropic turbulence and up to magnetic Reynolds numbers of 220, the foci results are accurate for the turbulent transport coefficients in the kinematic regime. If you consider an analysis at this regime where both the Reynolds numbers are small, the kinetic alpha obtained on the foci indeed captures the full nonlinear alpha effect. So both foci and tau approximation type closures give identical results. The force field correlation vanishes exactly for delta correlated forcing, but it cannot be ignored in general. Now, the bottom line, that the main point that I want to drive home is Lorentz forces cause the quenching of alpha. So if you want to get rid of all this, maybe you have to think about helicity fluxes or maybe Proctor's fluctuating alpha. So thank you.
Okay, we have time for lots of comments and questions. I suspect we might have them. Nathan first.
My first comment, that is very nice result, which demonstrates that all point of view is correct. It's very good. From another hand, I would like to stress, all this, approach gives the same just for small magnetic Reynolds number and hydrodynamic Reynolds number.
Yes.
If we go to real situation, unfortunately, at least today, just our approximation gives something more which is possible to compare with reality.
Or realization.
Yes, but it's in preparation.
Okay. Any more questions? Yes, David.
So you're calculating alpha when you've got a small scale dynamo.
Yes.
So you've got fluctuations which are growing exponentially.
Yes.
So the only sensible averaging procedure you can do is to have a box that is growing exponentially. You cut your results off when they were just about to become horrendous.
Yes, true.
So that quantity you're calculating is meaningless, absolutely meaningless. You've got exponentially growing fluctuations, and an average exists only if your box size covers that.
Yeah, but if you look at, if you don't go that far, I mean, so this is expressed in units of term over time.
It means nothing.
I mean,
you need bigger box. If the
Because
fluctuations remain
exponentially
small
growing
and
fluctuations.
fixed, you don't need
Yeah,
bigger box.
magnetic Prandtl number less than 1.
Yeah.
Magnetic Reynolds number less than 220. So I guess in this situation they hadn't any turbulent dynamo.
No, you don't. It does.
No, it has a small
It
scale.
has a small scale.
It has a small scale.
It has a small scale
Which is
dynamo.
growing
So by definition, U and V are growing exponentially. So the fluctuations that you're getting in the way of this measurement are growing exponentially.
So the statement if there are
So if you want to average them, you could have an exponentially growing
so
box.
if
In
there are,
non-linear regime.
if there are magnetic small scale dynamo, it is possible to perform such.
Yeah, because he
Yeah.
stopped it.
Yeah.
He stopped it because it was getting horrible.
Yeah.
And so what does it mean?
Yeah. But if we switch off a small scale dynamo, it's correct. Yeah?
Well, I'm talking about the case where the case he showed, RM220, there was a small scale dynamo, yes?
Yes.
But David, then they took into account not only induction equation but Navier-Stokes equation.
No,
They
that's the second.
separated this dynamo.
That's the second bit of
No,
the
I'm
talk.
talking about the beginning bit of the talk. The beginning bit of the talk, as I understand it, was purely kinematic calculation.
Let one of the people answer.
So it is an hypothesis that there are two things going on at the same time. One is the small scale dynamo, and the other one is what leads to an alpha effect. We have checked already for simple flows like the Roberts flow that once the magnetic Reynolds number becomes large enough, you do generate a small scale dynamo that leads to an oscillatory exponential growth, which does not affect the average once you average over this oscillatorily growing function. It just becomes very hard to compute, of course, meaningful averages once these fluctuations become so big. But the hypothesis that these two things are basically just a superposition onto each other is verified. And therefore we can say that if there is a plateau anywhere which looks reasonably good, then that's the value we have to take.
I don't know, I'd be very wary about looking at a function which is going to get with exponentially growing fluctuations, and you find a little flat plate and say everything's hunky-dory. I mean, I would believe that. That is not a valid averaging procedure. You've got to average over your fluctuations, and the fluctuations are growing exponentially. And so you better deal with it. And you deal with it by making your box grow exponentially. Even if it made sense, what would it mean?
No, I just wanted to point out that the mean field is like 1 in these units, and the fluctuating field at the end of the 25 steps is like 20 or something. And in fact, the peaks are like 100, 200, which is shown in our thing. No, so let me just finish. So if you go back to the alpha plot, you still get not, at that 25, the fluctuations are still not dominating. So my
It's not
message,
very strong fluctuations.
so my take from this at present is that even if the small scale dynamo is going berserk, okay, and the small scale dynamo generated field is about 20 times the mean field, that's up to that. I think you can see that you do get a mean which is near 1, and you get fluctuations which are not still going berserk. Of course, they will go berserk soon. They will go berserk soon. So because, and then you have to ask. So this is what I would like to understand: is the turbulent transport coefficient independent of what you calculate? But yeah, sorry. So or is it just that this alpha will only last for this factor of 20 in this particular case? So this is something which yeah.
In fact, I will, because of challenge. Okay, but if you'd started with an initial condition, which, it's a linear problem, so you'd start with an initial condition which was, 1,000 times bigger in kinematic calculation, with fluctuations in it, you might never have seen this bit where you can detect the mean. So, what does it mean?
No, here you are
Because your
starting everything
fluctuations would
weak.
always
Here you are starting everything in with some initial conditions.
Zero. The test field is the small scale B is zero initially. It is
Initially.
it's only driven by the imposed test field.
which has an amplitude.
Sure.
Which is an amplitude of 1. That's an
One.
arbitrary amplitude.
Yeah.
Exactly.
So now the thing is, because the small scale dynamo, the small scale field has grown quite a
So
bit
if you
bigger.
started with some power in a small scale field,
Yes.
then that could have grown and you might never have seen that before you got your alpha. Would that
Yes,
be fair?
but what I'm impressed by is that there is at least some factor of 20 in this particular case, before which these fluctuations are not yet going berserk.
But that's to do with the time it takes to find the eigenfunction of the exponentially
No,
growing
no.
solution.
Yeah,
Because
that's very
eigenfunction has been found right there.
At the time 5.
As you can see, it's growing exponentially in its growth rate flat. If you just look at the growth rate,
Yeah,
it's
5.
already growing exponentially from time, whatever, 5 or
5.
10 or something like that.
Yes.
So eigenfunction has been found.
But what level does the eigenfunction grow from? Some level, which is to do with your initial conditions. Sorry.
I have a comment. In principle, in order to prove that 4 approaches yield the same results, you don't need at all small-scale dynamo.
We're not talking
That's-
about that part of the talk.
There's 2 bits to the talk.
There's 2 parts to the talk,
Yeah.
and I'm stuck on part 1. We're talking about the cumulative estimate. We're not talking about sticking 4 different bits of the alpha together. We're talking about this. We're talking about calculation of a mean quantity in the present exponentially growing fluctuations and whether it makes sense. And furthermore, if you can distill an average out of something with exponentially growing fluctuations, what does it mean?
I can also ask the other way around. What do you think the result does actually mean if we do find a plateau for the time that the small-scale dynamo has not grown to infinity yet?
That's a good question, which is what I've just
I mean, is there any serious doubt that that what looks like an alpha effect is actually caused by something else?
Can I ask you a question?
In other words,
you
are they-
take your calculation of alpha when you do it. Are there any stages where you see something that may plateau a bit like that, and then?
No.
But you must do it kinematically. This is a kinematic
Well,
question
you've
here.
done kinematic
He has done
calculation.
kinematic, but it's a question of different flows also, I guess.
Yeah, they have impulse flows, specific impulse flows.
No. I'm talking
I'm
about
not-
convection.
Well, what does it mean? Okay, there's your alpha, it's a number, it's 1. Let's say. And I don't, I've already said a million times, I think it's a dodgy averaging procedure. But there you are, it's a number, it's 1. What does that mean?
Well, if you're using Fossa expression, it means that they are right, at least to this
No,
level.
I'm not using anybody's expression. What is it, what does...
No, if you want to stick it into a mean field model, you will put this alpha with these fluctuations, and the fluctuations will eventually go berserk, so you have to see what they will do to you.
That's a good
Yes.
question. So you say, right, so there's alpha is 1 and there's eta is something.
Right, also 1.
So you're postulating about a large scale thing which with growth rate alpha k minus eta k squared, which actually would be negative, but anyway. But that doesn't have to be k small, you have to get alpha k minus eta k squared. And you say, right, if I do the simulation, is that what I'll see? No, that's not what you'll see. What you'll see is this small scale dynamo.
Yes, so my question is, if you have this factor of 10 or 20 weaker mean field compared to the compared to what you'll saturate the small scale dynamo with, will you see something? I mean, this is why I want people to also look at finite large scale field, starting from finite fields.
Okay, yes. That's a good. Okay, do we have any comments on the second bit of the talk or any engine?
Just to change the topic, I mean, you have a very good analysis between
I can't hear you.
so you have a good analysis computing alpha and beta t in the first part of your talk. Have you ever thought about computing both of them in the nonlinear regime, somehow by extending?
No.
I mean, there's other methods. We have, there is, of course, the nonlinear regime has been studied over the last 5 to 8 years. And we know fairly well, I think, how the nonlinear regime can be described. Namely by a time-dependent catastrophic quenching formula, which does include mean currents, it does include time derivatives over alpha m, and it does include fluxes, divergences of fluxes.
This is 3D MST.
Yeah, of course. Yeah.
So is it agreed that there is a beta quenching in 3D?
There's a what?
Beta quenching.
Yeah. Is it
Beta
agreed?
quenching.
Beta quenching.
That's not known.
Is it agreed?
No, that's not conclusive yet, but Petri will have some results on that, and there's work on progress. So that's certainly something we hear about during the program, I hope. Fairly confident about this.
Okay. Anybody else?
I would like to attract attention to the other option. The analytics underlying all these investigations is applicable to ordinary differential equation with random coefficients. And dealing with such ordinary differential equations, you can reproduce billions of realizations, and we play such games with simple system of ordinary differential equations which mimic such kind of behavior. And we really did see that sometimes something what should be similar to alpha effect is reproducing only in the case of exponentially growing box, and sometimes it can be reproduced with a finite number of realization, with a finite box. It looks that both kinds of answers is possible, and at the moment I don't see any possibility to reproduce so huge bulk of computations in 3D numerics, and the reasonable way is to simplify the problem up to ordinary differential equation.
Yeah. I just have one comment about the second part of your talk. A while back, Keith Moffat did some calculations where he specified the thermal driving, and it calculated the alpha effect by specifying the statistics of the thermal driving. So he drove everything by convection, and then managed to calculate alpha, which seems that he had a very special case for alpha, I guess. So I don't know if you've related your results to his. Might be interesting to have a look.
I have another comment to the last part. The motivation, one motivation was to clarify, and that was actually from the Isaac Newton Institute meeting in 2004. A question came up, can one show that the first order smoothing approximation is correct even in the low magnetic Reynolds number limit? And back then it looked like that the tau approximation is actually invalid at low RM. That's how it looked like back then. And the problem is simply that one has to be slightly more careful in order to do the slope connectivity limit correctly. And then, of course, they do agree. So that was one relief.
Okay, I think we need to carry on.
But actually, you can
we get the next
rewrite this tau approximation. You'll be good.
The other thing you didn't mention, maybe, it didn't emphasize, you have a b to the minus 2 quenching for delta correlated forcing.
Yeah, steady forcing is b to the minus 3.
Yes. So that clarified a long-standing issue in the literature, of course. And Nathan and Igor had been finding this b to the minus 2 quenching all the time. And Moffat and Rüdiger did b to the minus 3 quenching.
It depends on model of tau.